Hello friends, welcome to the series of lectures of Mathematics 1. Myself Hardik Patel from LJ Institute of Engineering and Technology. In today's session, we are going to continue the Fourier series. In a last session, we have seen the Fourier series, introduction of the Fourier series. Now today's topic is a Fourier series for a continuous function with a period 2 pi. Correct? Now first of all, we are starting with the Fourier series for a continuous function on interval c to c plus 2n. Correct? So this we have already seen in the last lecture that fx is equal to a0 by 2 plus sigma n running from 1 to infinity an into cos n pi x upon l plus bn into sine of n pi x upon l, and where a0 is given by 1 upon l c to c plus 2l fx dx, an is equal to 1 upon l integration from c to c plus 2l fx into cos n pi x upon l dx, and bn is equal to 1 upon l integration from c to c plus 2l fx into sin n pi x upon l dx. Now we are starting with a 2 pi periodic function, correct? So in that case, if we are starting with a 2 pi period, now we are starting with a 2 pi periodic function. So if you have 2 pi is the period of your interval, that means you have 2l is equal to 2 pi, correct? That will give al is equal to pi. See, the first thing you have to do, you have to find out what is the value of L. And to find the value of L, suppose you have given any open interval a to b or closed interval a to b or any open closed interval, then in that case we have b minus a is equal to 2L. Correct? That means second minus first. That will be a 2L. Here we are starting with a 2 pi periodic function. So b minus a is 2 pi, and that will give 2L is equal to 2 pi. So that will give L is equal to pi. Now if you are going to put L is equal to pi here, then pi will be cancelled out, and this integration is going to be reduced in the form of an cos nx plus bn sin nx. And here you have 1 upon pi c to c plus 2 pi fx dx. Here you have an is equal to 1 upon L, 1 upon pi integration c to c plus 2 pi fx into cos nx dx, and bn will be 1 upon pi c to c plus 2 pi fx into sin nx dx. Okay. Now we are going on to the example. Find the Fourier series of fx is equal to x square on interval 0 to 2 pi, and hence prove that pi square by 12 is equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square minus so on and so on. So the Fourier series is given by fx is equal to a0 by 2 plus sigma n running from 1 to infinity. Since this is the total length is 2l, so 2 pi minus 0 is equal to 2l, and that will give 2 pi is equal to 2l, and that will give l is equal to pi. So in above equation we are going to substitute L is equal to pi. That means your Fourier series is going to be reduced in the form of a0 by 2 plus sigma n running from 1 to infinity an cos nx plus bn sin nx, where an will be 1 upon pi c to c plus 2 pi. That means interval is 0 to 2 pi. So 0 to 2 pi fx dx. But fx is nothing but it is x square. And if you are going to integrate x square, then it has an integration x cube by 3. Now limit is from 0 to 2 pi. So substitute the limit, that will give you 2 pi cube by 2 pi whole cube by 3 minus 0. And if you are going to substitute the value, then you will have 1 upon pi into 8 pi cube by 3. So pi cancel out, and a0 will be a 8 pi square upon 3. Correct? Now we are going on to an. An will be 1 upon pi integration from 0 to 2 pi fx into cos nx dx. Correct? So fx is your x square, cos nx that will be a remains as it is. Now we are going to apply u into v, that means continuous integration by parts. So this will be your u, this will be your v, u as it is, that means x square as it is. Integration of cos nx is sin nx upon n. Correct? Then minus into the bracket derivative of x square, that will be a 2x, and again integration of sine n pi nx by n, that will be a sine as an integration minus cos nx upon n, into n is already there, so it will be minus cos nx upon n square. Then again derivative of 2x will be 2, and again integration of minus cos, that will be a minus sine nx upon n cube. Correct? Limit is from 0 to 2 pi. So simplify this term, that will give x square sine nx upon n plus minus minus plus 2x into cos nx upon n square plus minus 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 2 into sine nx upon n cube. Limit is from 0 to 2 pi. Correct? Now first put the limits, and sine 2n pi has a value 0, that we have already discussed in the last lecture. Sine 2n pi has a value 2n pi has a value 0, and cos 2n pi has a value 1. So if you are going to substitute 2 pi here, then this term is 0, this term is 0, and this term is going to be 1 upon n square. And whenever you are going to put x is equal to 0, then this term is 0, this term is 0, because 0 into anything, 0 into anything, 0, and sine 0 also has a value 0. So all the terms of lower limits are going to be 0. So simplifying this one, you will have 1 upon pi into the bracket 4 pi upon n square. So pi will be cancelled out, and you will have 4 upon n square. So this is the value of a. Same manner, bn will be 1 upon pi integration from 0 to 2 pi fx into sine nx dx. Now fx is x square, so put it and applying in continuous integration by parts. So x square, it is going to be considered as a u, and sine nx is going to be considered as a v. So first x square as it is, and sine has an integration minus cos nx upon n. Then the derivative of x square, that will be a 2x, and minus cos nx upon x has an integration minus sine nx upon n square. Then 2x has a derivative 2, and minus sine nx upon n square has a minus minus plus cos nx upon n cube. Okay, and limit is from 0 to 2 pi. Done. Now simplify this term, that will give you minus of x square into cos nx upon n plus 2x into sine nx upon n square, because minus minus plus, and plus 2 into cos nx upon n cube. Limit is from 0 to 2 pi. Now if you are going to put 2 pi, then cos 2n pi has a value 1. So this value is going to be 1, this value is going to be 1, and this value is going to be 0, because sine 2n pi has a value 0. So here you have, for upper limit, you have minus 2 pi whole square, that is 4 pi square into 1 upon n, plus this term will be 0, and this term is going to be 2 into 1 upon n cube. Minus, whenever you are going to substitute 0, then this term is 0 into anything will be 0, 0 into anything will be 0. So first two terms are 0. And cos 0 has a value 1, so you have 2 into 1 upon n cube. Okay. Now we are going to simplify these terms. So you will have minus 4 upon 4 pi square by n plus 2 upon n cube minus 2 upon n cube. So plus 2 upon n cube minus 2 upon n cube cancel out, and you will have 1 upon pi into the bracket minus 4 pi square by n. Pi cancel out one time, and that will give you minus 4 upon 4 pi upon n. This is the value of bn. Now put this a0, an and bn in Fourier series. That will give you a0, an and bn. So putting these values, that will give you the Fourier series fx is equal to 1 upon 2, because a0 by 2, so 1 by 2 into 8 pi square by 3, plus sigma n running from 1 to infinity, an, that is 4 upon n square into cos nx, plus bn, that is minus 4 pi upon n into sin nx. And if you are going to simplify this, then 2 4 is 8, so you will have 4 pi square by 3. In both of the, so we are going to separate these both terms and constant common out. So here 4 common out, and you will have plus 4 into sigma n running from 1 to infinity cos nx upon n square, minus here 4 pi common out, and you will have sigma n running from 1 to infinity sin nx upon n. So this is the Fourier series of your function x square, correct? So this is the Fourier series for x square. And if you are going to write down this in a series form, that means put n is equal to 1, n is equal to 2, n is equal to 3. So you will have cos 1x upon 1 square plus cos 2x upon 2 square plus cos 3x upon 3 square. Same manner here you have sin 1 upon sin 1x upon 1 plus sin 2x upon 2 plus sin 3x upon 3 and so on. So this is your Fourier series. Now we are going on to the deduction. Once this is our Fourier series which we have written in above page. Now we have to prove that pi square by 12 is equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square and minus so on, so on, so on. That means you require the terms with a square in denominator, correct? So we are going to put x is equal to pi. See, we require these terms with squares as well as we require the alternative sign, correct? Alternative sign is there. So if you are going to put 0, then cos 0 is going to be 1 and each term is going to be 1. But we required alternative sign, so we are going to put it as a pi. So pi is in between your interval 0 to 2 pi. So putting value pi, sin n pi is going to be 0. So these all terms are going to be 0. So left hand side is going to be a pi square is equal to 4 pi square by 3 plus 4 into cos pi upon 1 square plus cos 2 pi upon 2 square plus cos 3 pi upon 3 square and so on. Now this 4 pi square by 3 is going in opposite side. So you will have pi square minus 4 pi square by 3 is equal to 4 into minus 1 upon 1 square plus 1 upon 2 square minus 1 upon 3 square and so on. Simplifying this term, so you will have 3 pi square minus 4 pi square, that will be a minus pi square by 3. And common out minus from this term, that will give you minus 4 into 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square and so on. So minus minus will be cancelled out and 4 is going in denominator, that will give pi square by 12 is equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square and so on. So whenever you have some deduction, at that time you have to put some particular value of x in this equation. Please remember this thing. That means you have to put some particular value of x in a Fourier series and then you have to simplify it. Okay. Now we are going to check out one more example. Find the Fourier series of the periodic function fx is equal to x minus x square on the interval minus pi to plus pi. And hence prove that pi square by 12 is equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square and so on. Again, you have interval from minus pi to plus pi. So if you are going to put the value of L, then you will have pi minus minus pi is equal to 2L. And that will give you 2 pi is equal to 2L. And that will give you L is equal to pi. So your series is reducing in the form of a0 by 2 plus sigma n running from 1 to infinity an cos nx plus bn sin nx. Now a0 is nothing but 1 upon pi integration from minus pi to plus pi fx dx, correct? So 1 upon pi integration from minus pi to plus pi x minus x square dx, fx is your x minus x square. Integrate this, so you will have x square by 2 minus x cube by 3 and limit is from minus pi to plus pi. First upper limit, so you will have pi square by 2 minus pi cube by 3 and then lower limit, so minus pi square will be pi square and minus pi square, that minus pi the whole cube, that will be a minus of pi cube. So here you have plus pi cube by 3. Simplifying this term, so pi square by 2 will be cancelled out and you will have pi square by 2 will be cancelled out and you will have minus 1 by pi into minus 2 pi cube by 3. So 1 pi will be cancelled out and the answer is going to be a minus 2 pi square upon 3. Same manner in an, we have 1 upon pi integration from minus pi to plus pi fx into cos nx dx. Okay. So 1 upon pi fx is you are nothing but x minus x square into cos nx dx. So applying u into v, So x minus x square as it is. Integration of cos is sin nx upon n. Then derivative of x minus x square is 1 minus 2x. Again integration of sin is minus cos nx upon n square. This again derivative of 1 minus 2x, that will be a minus 2. And again integration of minus cos nx upon n square, that will be a minus sin nx upon n cube. Okay. Limit is from minus pi to plus pi. Now sin n pi, first simplify this term. So you will have x minus x square into sin nx upon n, minus minus plus 1 minus 2x cos nx upon n square, plus minus minus plus. So you have plus 2 into sin nx upon n cube. Limit is from minus pi to plus pi. Now if you are going to put the values, then sin n pi has a value 0. Sin n pi has a value 0. So these two terms are going to be 0 for upper limit. And cos n pi has a value minus 1 raised to n. So this 0 plus 1 minus 2 pi into minus 1 raised to n upon n square. This term will be 0. Minus lower limit sine of minus n pi, that will be again 0, plus minus my sine cos minus n pi will be cos n pi, because cos minus theta is cos theta, and that will give you cos n pi has a value minus 1 raised to n. So you will have 1 minus minus plus 2 pi into minus 1 raised to n upon n square, plus 2 into sine n minus n pi, but it has a value 0. So if you are going to simplify, then you will have 1 upon pi into the bracket 1 minus 2 pi into minus 1 raised to n upon n square, minus 1 plus 2 pi into minus 1 raised to n upon n square. Minus 1 raised to n upon n square common out, and you will have 1 upon pi into minus 1 raised to n upon n square into the bracket 1 minus 2 pi minus 1 minus 2 pi. So 1 minus 1 cancel out, and you will have minus 4 pi upon this. So minus 4 pi, from that pi will be cancelled out, and if you are going to simplify, then you will have answer minus 4 into minus 1 raised to n divided by n square. Correct? This is your answer of an. Now bn. Same thing we are going to do for bn. 1 upon pi minus pi to plus pi fx into sin nx dx. So 1 upon pi fx is x minus x square into sin nx dx. Now applying u into v, so x minus x square as it is, sin nx as the integration minus cos nx upon n, minus derivative of 1 minus x square, that will be a 1 minus 2x, and minus cos nx upon n as the integration minus sin nx upon n square, plus 1 minus 2x as a derivative minus 2, and again integration of this term, that will be a cos nx upon n cube. Limit is from pi to minus pi to plus pi. Now substitute the limit. So first simplify and write it again. So minus minus plus, minus plus minus. So you will have minus of x minus x square cos nx upon n, plus 1 minus 2x into sin nx upon n square, minus 2 cos nx upon n cube. From limit is from minus pi to plus pi. First we are going to put upper limit pi, that will give you pi minus pi square, cos n pi is minus 1 raised to n upon n. Sin n pi is 0, so this term is 0. Second term, minus 2 into cos n pi, that will be minus 1 raised to n upon n cube. Minus lower limit, minus of lower limit into the bracket, minus of minus pi into minus pi square, cos minus n pi will be minus 1 raised to n upon n, minus 1 raised to n, so you will have minus 1 raised to n upon n, plus sin minus n pi is a value 0, and cos minus n pi has a value minus 1 raised to n, so you have minus of 2 into minus 1 raised to n upon n cube. Now we are going to simplify these terms. So separate the terms with minus 1 raised to n common out from these two. So that will give you minus pi minus minus plus pi square minus pi minus pi square. So plus pi square minus pi square cancel out. Same manner from these two terms you have minus 2 and plus 2 will be cancel out. So the remaining terms you have 1 upon pi into minus 1 raised to n upon n into minus 2 pi. Pi will be cancelled out and the answer will be Bn is minus 2 into minus 1 raised to n upon n. Now put this value in the Fourier series. So you putting this all values in the Fourier series. So the Fourier series expansion we have is 1 upon 2 into a0 is minus 2 pi square by 3 plus sigma n running from 1 to infinity into the bracket an is minus of 4 into minus 1 raised to n upon n square cos nx plus bn is minus of 2 into minus 1 raised to n upon n, okay, into sin nx. And if you are writing this in a simple form and separating the terms, then you will have minus pi square by 3 minus 4 into sigma minus 1 raised to n cos nx upon n square minus 2 into the sigma minus 1 raised to n sin nx upon n. If you are writing this term in a series form, that means put n is equal to 1, 2, 3, 4, then you will have series minus pi square by 3 minus 4 into minus cos 1x upon 1 square plus cos 2x upon 2 square minus cos 3x upon 3 square and so on. Minus 2 into minus sine upon 1 plus sine 2x upon 2 plus minus sine 3x upon 3 and so on. And now you have to evaluate, you have to prove that pi square by 12 is equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square and so on. So see, you have to make these terms 0. And here it is already alternative sign is there. So we are going to directly substitute x is equal to 0. Correct? So we are going to put x is equal to 0 and that will give you left hand side is 0 is equal to minus pi square by 3. Cos 0 has a value 1, 0 has a value 1 and sin 0 has a value 0. So you will have minus 4 into the bracket minus 1 upon 1 square plus 1 upon 2 square minus 1 upon 3 square and so on. Now this pi square by 3 going in opposite side, that will give pi square by 3 is equal to here minus common out. So you will have 4 into the bracket 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square and so on. Divide it with 4 and that will give you pi square by 12 is equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square and so on. Okay. So these are the topics which we have covered in today's session. So if you have any query or any doubt regarding these topics, then please feel free to contact me. These are the some of the examples which you have to do yourself. If you have any doubt in this, then also you can contact me. Thank you so much.